So, my Lennard-Jones potential, also known as the LJ potential, this is how we will term, is defined as the interaction energy or the potential function phi of rho to be minus A of rho times rho to the power minus m plus B of rho times rho to the power minus n, okay, where my A represents the attractive component, because of the minus sign, and B represents the repulsive component, okay, because of the plus sign. Okay. So, then and my rho is the distance between two atoms or the atoms under consideration or the structures under consideration. And then typically these coefficients m n, these are natural numbers. So, sometimes these are also called as the Lennard-Jones M n potential, which tells us what is the strength of the attractive as well as the strength of the repulsive components of the potential. Okay. So, for example, if my m is equal to 6 and n is equal to 12, which is the most common occurrence of Lennard-Jones potential in almost all the physical models that are used, also known as the 612 LJ potential, okay, right. So, and so let me term is as example A. Another potential that is frequently used is the 510 potential, for example, to describe hydrogen bonding, okay, hydrogen bonding. Also, well, the 512, but well, the hydrogen bonding, not this 512, but in fact 1012 potential, sorry about that. So, this is the 1012 LJ potential, okay, frequently used to model the hydrogen bonding. For example, so if I were to plot the LJ potential, let us look at the plot, right. So, I have rho times L of rho, and notice that this is let us see, if we were to plot the following function, let us say phi of rho given by 4 epsilon, these are all constants, epsilon minus sigma by rho to the power 6. So, my A is sigma to the power 6 plus sigma by rho to the power 12, where my epsilon and sigma are, well, sigma are constants, right, and they are real constants. Then if I were to plot this LJ potential, I see that this looks like the following. Okay. So, where we in this part of the potential we have the repulsion, and in this part of the potential represents the attraction, the attractive potential, right. So, in particular we also see that, well, if I were to draw this slightly more carefully, so this is like the following, okay, again, well, again. So, this is slightly slanted and then it turns like this, and it in fact it goes to 0 as r goes to infinity. Okay, we will see that. So, for this potential we definitely have the minima, and the minima here is given by the epsilon, where epsilon is also known as the potential depth or the well depth, okay, also known as the energy well depth. Okay. So, suppose I model my carbon nanotube with Lj potential, then my well depth will denote this parameter epsilon as shown in this example. Okay. So, epsilon is the well depth and sigma is the distance from 0 to this minimum of the Lj potential. So, sigma is the van der Waal distance, van der Waal distance, and it turns out to be b by a to the power 1 by 6. Well, all we have to do is just take the derivative of rho and set it equal to 0, and that will give me my rho star or critical value, which is sigma. Okay. Okay, so these are this is a typical example of the Lj potential that we will be using. Okay, so we can see that van der Waal interactions are usually short range interaction. Why? Because notice that as rho goes to infinity, the interaction nearly goes to 0, right. So, in fact, I would say that the Lennard-Jones potential represents a medium range interaction, because well, short range repulsion, but medium range attraction, which means that if I have that rho goes to 0, then I can see that we are in the repulsive range. If rho goes to infinity, then it is very weakly attractive. Okay. And in the intermediate range, we have some reasonable attraction via this potential. Okay. So, what I said is the following. So, van der Waal interaction in general, van der Waal interaction energy in general is a short range interaction energy. Models only nearest neighbor, interaction, and ideally modeled by Lj potential. We have seen that all these properties of van der Waal interaction are quite appropriately captured by Lj potentials. Okay. And these are typically, this van der Waal interaction energies are typically applied to non-bonded non-polar structures. Okay. So, these are very different than ionic interactions or covalent interactions. Okay. So, then let me start our basic modeling effort by looking at the interaction of a point with a plane, for example, a carbon atom with a graphene sheet. Okay. So, I am going to step by step build up the model, where eventually we are going to look at the oscillatory mechanics of two carbon nanorods. Okay. So, let me look at the first of the example to discuss. So, find the interaction energy E and the van der Waal force, F d F v d w for a single carbon atom, a distance z from an infinite graphene sheet. Okay. So, what have we got is the following. So, we have a graphene sheet where the sheet contains these tessellated hexagonal rings, right, and so on so forth. And then we have a carbon atom which is sitting on top, well, it is on top of this sheet, and we want to model the interaction of this carbon atom with the sheet, right. So, assume to model this interaction, let me place this carbon atom at a convenient location to the sheet. So, we are going to assume that the carbon atom coordinate is 0 0 z. The carbon atom coordinate is 0 0 z and the position. So, this is z is the distance of the carbon atom from the sheet and the sheet is on the xy plane and the position. So, these are my assumptions. The position of the sheet is given by the xy plane xy 0, right. So, which means rho, which is the distance between the carbon atom, rho which is the distance between the carbon atom and the graphene sheet, is given by square root of x square plus y square plus z square. Okay. So, that is my rho. Okay. So, then let me model the interaction or the van der Waal interaction of this atom with the sheet using our Lennard-Jones potential or the 612 potential. Okay. So, using Lennard-Jones 612 potential, I see that my interaction energy is E, which is eta of double integral from minus a by x square plus y square plus z square to the power well, this was half times 6 gives me to the power 3, right. So, this is my rho to the power 6, right. So, rho had a square root, okay, plus b times x square plus y square plus z square to the power 6. So, this is my rho to the power 12. So, 612 potential and times dx dy. Okay. So, this is my interaction energy. Note that eta here, the constant sitting outside, is the average number of atoms per unit area of the graphene sheet. Okay. Graphene sheet. Okay. Fine. So, we are calculating the average interaction energy. Okay. Now, all I have to do is to evaluate this double integral, right. I can write down this double integral as eta times double integral, well, eta times negative a. So, assume that a and b are, assume a and b are my constants. Okay. A and b are my constants. So, my integration is minus a I 3 plus b I 6, right, and where my I n is my double integral from minus infinity to infinity times dx dy by x square plus y square plus z square to the power n. Okay. So, all I do is I evaluate this I n for a general n, plug n equal to 3 and 6. Notice that the factor x square plus y square plus z square tells us that we should use the cylindrical polar coordinates. Z is fixed. So, the only variables in our integration are r and theta. So, we are going to use cylindrical polar coordinates with z fixed. So, changing to polar coordinates, because z is fixed, I see that my I n turns out to be integral from 0 to 2 pi d theta times integral r from 0 to infinity, right, times r dr divided by r square plus z square to the power n. Okay. And now, this integration is fairly simple. So, let me write down the answer. This is pi by n minus 1 times z to the power 2 n minus 2, right. Okay. So, that is my I n, and then from here I can plug all these values and I see that my interaction energy is eta times pi times minus a by 2 z to the power 4 plus b times b by 5 z to the power 10, right. Okay. So, from here I can calculate my van der Waal force. I need to differentiate with respect to z or the axial coordinate. So, my van der Waal force F v d w turns out to be minus partial E partial z, which is pi eta times minus 4 a by 2 z to the power 5 plus 10 b by 5 z to the power 11, right, which is also equal to let me just rewrite the following. So, this is 2 pi eta times negative a by z to the power 5 plus b times z to the power 11. Okay. So, that is my van der Waal force. So, typically the values of these constants for a graphene sheet are follows. So, typically for so again these are from standard physical chemistry textbooks. Typically for graphene sheets I see that my A is given to be 17.4 electron volt angstrom 6, and B the constant is the quantity this electron volt, and my constant eta comes out to be 0.3812 atom per angstrom square. Okay. Okay. We see that for all these constants, let me just quickly plot my interaction energy and my force. So, my x coordinate is the axial component z, z is in angstrom, and typically I see that my interaction energy will be the following. If z is positive and if z is negative, I see that the interaction energy will be having the following. So, the interaction energy is an even function of z, right. So, these are my curves for E, right, and if I were to plot the force, I see that the force follows the following curves. So, the force is also the maximum at the same point where the energy attains the minimum, right. So, F z and the force in the other half is as follows. So, this becomes the following, right. So, notice that, so these are my force curves, this one here. Okay. So, what I am trying to show is my force curve is antisymmetric because of the odd terms here, and my energy curve is symmetric because of the even terms, and hence we can see that the minimum or the maximum force is given by the minimum of the energy curve, okay, and vice versa. Okay. So, then I would like to go one step further and calculate the interaction energy of two parallel graphene sheets, right. So, the next problem that I want to highlight, find the interaction energy of two parallel infinite plates of graphene, two parallel infinite plates of graphene at a distance z. So, the graphene sheets are separated by separated, I should write the word separated by a distance z, right. Now, so we have two infinite sheets of graphene and I want to find out. So, these are all z tending to minus infinity, z tending to infinity, and I want to find the interaction of these two infinite sheets. Now, notice that when we found out the interaction of a point with a sheet, we got a finite answer, which means that if I were so the natural way to model this setup is we sum up the point sheet interaction. Now, on 2 infinite sheet there are infinitely many points, which means that we are doing an infinite sum of a finite quantity or an infinite sum of the point sheet interaction, and we expect the answer to be infinite. So, instead of finding the answer that is the interaction energy of 2 infinite sheets, I am going to find out the answer as the interaction energy of 2 infinite sheet per unit area of the 2 sheets. Okay. So, I am going to find out the interaction energy per unit area to get a finite answer. Okay. So, as I just said the following, the interaction energy is an infinite sum of a non vanishing term and it is infinite, right, is an infinite sum of a non vanishing term and it is infinite. So, we instead calculate the interaction energy per unit area. So, we calculate the interaction energy per unit area. Okay. So, let me just introduce the concept of eta. So, I denote my number of atoms per unit area, the number of atoms per unit area as eta, and each atom interacts individually. Each atom interacts individually with the other plane, with the other plane. Okay. Now, so which means that my interaction energy per unit area, let me denote it as EPUA per unit area, E of per unit area will be the answer that we found in example number 3. So, the answer was pi eta times this quantity times eta, where eta is the number of atoms of the second sheet per unit area, right. So, this is eta times E, where E is found in example 3 that we discussed few minutes back, and let me write down the answer. So, this is pi eta square times minus a by 2 z to the power 4 plus b by 5 z to the power 10, right. Okay. So, we take A to be 15.2, B to be 24100. These are typical values. These are typical values of graphene sheet interaction. And what we find is the following. We find that eta is the same. So, eta is same as in example 3 that we have discussed few minutes back. We find that the equilibrium spacing between the 2 sheets. So, how can we find the equilibrium spacing between the 2 sheets, the static equilibrium? By minimizing the force, right, or finding the force or minimizing the energy. So, nature is going to provide us with the equilibrium when the energy of interaction is minimum, right. So, it turns out that the equilibrium spacing between 2 sheets given by P, spacing, let us say P V D W is denoted as the energy the derivative of the energy with respect to z E p u a, differentiate and set equal to 0. From here I get that my equilibrium spacing z naught turns out to be b by a to the power 1/6, and that comes out to be 3.41 angstrom. Now, what is the issue here? The issue is that experimentally the values that are reported by these physical chemists, that is the on the equilibrium spacing of these sheets, is slightly lower. So, experimentally z naught is reported to be z naught equal to 3.35 angstrom, right. So, z naught is reported to be 3.35 angstrom, although close, but it is roughly it is quite a bit of different than the values that we have found through our model. So, this question that is asked is, where is the discrepancy in our model, and the discrepancy lies in the structure of graphene itself. We know that graphene has parallel sheets which are almost equidistant apart. So, which means that any point on one sheet of the graphene not only interacts with its nearest graphene sheet, but also interacts with all the other graphene sheets which are at distance z, 2z, 3z, 4z and so on so forth. So, we must include all those other graphene sheets which are at a larger and larger distance away from the sheet under consideration. Okay. So, this is the issue that I want to highlight. So, the reason for the discrepancy is that graphite atoms interact not only with its nearest neighbor, neighbor planes, but with all other planes, not only with its nearest neighbor planes, but with all other planes. Okay. So, which means that we have to incorporate the effect of all other graphite sheets that we have ignored, which are lying parallel to each other, right. So, the new model in our graphene structure is, we assume that there exists an infinite sheet such that the number of planes are all separated by the same distance. They are all separated by the same distance. Let me call this distance as z. So, one sheet is separated from the central sheet by z, the other also by z and so on so forth, right. So, if we were to find the total distance, they become z, 2z, 3z and so on so forth, right. So, which means that my total interaction energy will be the sum of each of these plates. So, that becomes E, which is pi times eta square times summation n from 1 to infinity of minus a by 2 times n z to the power 4 plus b times 5 n z to the power 10, right. And then there is a multiplication by 2. Notice that this is the same, we are summing up the same quantity that we had introduced in our previous expression. Notice this expression, and now instead of this expression I have replaced by z, 2z, 3z and so on so forth, right. So, inside the sum I have the same expression at different distances, and outside I have also introduced a factor of 2, because each sheet interacts with the sheet above, above and below. So, the 2 is to take into account the sheet interaction above it and below it, otherwise we have to sum n from minus infinity to plus infinity, right. Okay. So, then this particular summation becomes 2 pi eta square times minus a by z to the power 4, well 2 z to the power 4, which is a constant, times summation n from 1 to infinity of 1 to the 1 by n to the power 4 plus b of 5 z to the power 10 times summation n to the power 10 n from 1 to infinity of this quantity. Notice that this is the this particular summation is the famous Riemann zeta function evaluated for n equal to for 4, and the second summation is the zeta function evaluated at 10. Okay. So, we know that, so again I am just rewriting these ideas. So, where my summation 1 by n to the power m is my Riemann zeta function of m, Riemann zeta function, okay, and my zeta of 4 is pi to the power 4 by 90. I am just plugging in the writing the answers, and the Riemann zeta function evaluated at 10 is pi to the power 10 by this quantity 93555. Okay. So, again I have picked up the handbook of mathematical functions and found out these values. Now, finally, when we differentiate this interaction energy with respect to z and set it equal to 0, I see that my z naught this time is going to be b by a times the zeta function at 10 by the zeta function at 4 to the power 1 by 6, right, and this gives me, after plugging in all the values for b a as described previously, this gives me z naught to be 3.37 angstrom. Notice how close is this value to our to the experimentally reported value. So, it turns out that the model had to incorporate certain additional term to realistically simulate the experiments. So, I am going to continue my discussion on the modeling of the oscillatory motion of carbon nanorods in my next lecture by slowly building up this example, and towards the end of the next lecture I am going to look at the variational form or the Hamilton's formulation of the oscillatory motion of carbon nanorods. So, thank you very much for listening. Thanks a lot.